We talked about matter, splitting it up into these categories and trying to figure out which things fit in which categories. Today we're going to talk about kind of the other side of that, which is energy. Have you heard of energy?
Yeah.
What is energy?
Waves.
Waves? Okay, yeah, that's a type of energy. That's electromagnetic energy. Sure.
Something that can create change.
Something that can create change. I like that, yeah. Yeah, that's the idea. Is energy is a sort of a capacity. It's a capacity to either do work or transfer that energy to do something, to change something. We usually define energy in the physics term of the capacity to do work. Or to act on something. From a physical standpoint, I could say that I have the energy to lift my bottle up in the air. That's doing work. I have transferred energy from me to the bottle by lifting it up in the air, and that bottle can then transfer its energy up to the surroundings by dropping that same distance. And so that's one way we think about energy with work. And if you ever go on and take some physics or just learn about some physics, there'll be all kinds of ways that can happen and how we measure it and blah, blah, blah. In chemistry, we also think about doing work with energy, but we more often are concerned with energy and heat. So there are two ways to transfer energy. Whoop. Heat and work. The work one we just described by moving the position of something, changing its position. Heat is something we experience probably even more obviously, that you can transfer energy through heat. If I pick up a cold piece of metal, let's say, how would you describe the energy flow that happens when that cold piece of metal is in my hand? Yeah, go ahead. How would you describe it?
I like words.
Okay.
The cold lowers your body temperature, or your temperature of your hand, I guess.
Okay, so yes, that would be an effect that the temperature of your hand would go down.
It's like convection.
So then how is the energy being transferred? Where is the energy coming from and where is it going to in that example?
Well, are you warming up the metal, or is the metal cooling?
That's the question. So those are kind of the two choices, right? Is the metal cooling your hand, or is your hand warming the metal? And the answer is they're both happening, but what describes how the energy is? Does energy carry with it cold, or does energy carry with it heat, I guess is another way of thinking of it. So would we say that something that is cold has more energy than something that is hot? Or something that is hot has more energy than something that is cold? Hot has more energy than cold. So that means that the energy transfer, the direction of the energy transfer must be from your hand to the cold object. So the energy from your hand flows into the cold object. This has the effect of raising the temperature of the object and cooling the temperature of your hand. All right, so that's the idea of energy flowing via heat. In a chemical reaction, we often talk about two different ways that heat flows through a reaction. And I don't know if you've heard these words or not. Exothermic and endothermic. Have you heard those words? What do you think they mean? How do you think they relate to what we just talked about? Yeah. Exo like exiting, yep. And endo taking in. Yeah, absolutely. So what this is talking about, and therm meaning heat. So an exothermic process is one that releases heat to its surroundings. So that's a process where the heat is flowing from something to the surroundings. And the way that we say that in chemistry is heat flows from the system to the surroundings. Often in chemistry, the system is the molecules or the chemicals that we're dealing with, and the surroundings is everything else, the solvent, the container, the air, everything that's not the chemicals. And so in an endothermic process, it's the opposite. Heat flows from the surroundings into the system. The tricky part about this is this idea of system and surroundings is arbitrary. We get to decide what's the system and what's the surroundings. There's no official rule for that. So if we take our example, a cold piece of metal, put a cold piece of metal in my hand, is that an endothermic or an exothermic process? The answer is it's both. It depends if you care about the metal or if you care about the hand, which one we define as the system. If the metal part is the system, then we would say, well, heat is flowing into the metal, right, from my hand. So that would be an endothermic process. But if our system is my hand, then the heat is flowing away from the hand into the metal, and that would be an exothermic process. So there's not a clear answer unless you define what that system is. But let me give you an example where it does get a little bit clearer. And this is where we would use it more practically. So let's say we have a chemical reaction in some beaker or something. And we put our chemicals in. They start reacting. And then we notice that it's starting to feel hot. We put our hands up to it, and it feels hot. Would you call that an exothermic process or an endothermic process?
Thanks.
Yeah, we would experience that as exothermic, because when we're dealing with a chemical reaction, our system is always going to be the chemicals, the reaction itself. So the fact that the surroundings are getting hot means heat is being transferred, energy is being transferred from the, and actually we should really say energy is being transferred via heat from the chemicals out to the surroundings that we can feel. So that would be an exothermic process. An endothermic process is one that we don't experience quite as much, but it would be you do your reaction. I don't even really know how to show this with pictures, but basically it would feel cold. Has anybody ever done a chemical reaction that feels cold? It doesn't come up a lot. One place that you can do this, and we will do this in lab, but one place you might see this, they have these instant cold packs. You know what I'm talking about with those? They're these little packages, and they're just seem like a package of whatever, but then you kind of break them all up, and then they get really cold. That's an endothermic reaction. The chemicals inside that are sucking energy in from the outside, and that makes it feel cold. All right. So how do we measure heat? Degrees. We use a thermometer, right? We measure temperature. But temperature is actually not the same as heat. We talked about heat is a transfer of energy, and temperature is a measure of that energy. So temperature, as we'll learn when we talk about gases, is a measurement of an average energy level of molecules. But it's not, we'll put of in quotes, because it really, a better way to say it is that the measure correlates to the average energy. That's why our temperature scale is not the same as an energy measurement. And I'll show you what that means in a second. We measure temperature in its own kind of scale, right? We have these degrees. And I want to show you how the different temperature scales relate to each other. Hopefully I can make this picture big enough that you can see it and it makes sense. This is from the book, so you can look at it also. You see those all right? So here are 3 different thermometers measuring in 3 different temperature scales: Kelvin, Celsius, and Fahrenheit. Have you used those scales before? All 3 of them? What haven't you used? Kelvin? Yeah. But we use the other one too, so that's good. Well, I guess we've all probably used the other 2 because we just used Celsius in lab the other day, right? And we use Fahrenheit more in our day-to-day lives with like room temperature. That's kind of unique to this country. But these are different scales and they have different attributes. One thing that's nice about this particular diagram is you see the levels of kind of some landmarks. And I always think it's a good idea to keep some landmarks in your head on these different scales about what happens. So boiling point of water, 100 degrees C, 212 degrees Fahrenheit. Normal body temperature, 37 degrees C, 98.6 degrees Fahrenheit. And freezing point of water, 0 degrees C, 32 degrees F. If you know those, then when we start doing some of these conversions and thinking back and forth in the scales, we'll have a sense of whether or not a measurement makes sense. So if I say something like, how many, we'll talk about the equations in a minute, but how many degrees Fahrenheit is 80 degrees Celsius? If you go through and do the calculation and you come up with 80 degrees Celsius is 500 degrees Fahrenheit, you should be able to look at that and say, wait a second, that's not right. Because 80 is below the boiling point of water, and boiling point of water in Fahrenheit is 212, and I'm getting 500, so something's wrong here. You know, so you have a sense of like whether your answer makes sense or not. So let's talk about this Kelvin scale, because that's kind of the weird one. What is important about the Kelvin scale, or what is special about it? Does anybody know anything about the Kelvin scale?
I think 0 is referred to as absolute 0, whereas like no living can exist.
Yeah, well, actually, it's right. I think no living can exist a bit higher even than that.
Just like
but yes, that's right. So absolute, the special thing about the Kelvin scale is that there is no negative in Kelvin. 0 is called absolute 0. The measure of average energy is an average kinetic energy of molecules, which is talking about molecular motion of atoms. Atoms are always moving, even in a solid. But at absolute 0, 0 K, 0 Kelvin, there is no molecular motion at all. And that has not been reached here, like scientifically. You can't cool something down to that. We get really, really, really close, like 0.0000001 Kelvin, but actually stopping molecular motion, there's all kinds of physics laws about what you have to do for that to happen. I don't know all the details of it. But it's called absolute 0, so there can be physically nothing lower than that. And that's what's special about the Kelvin scale, is it stops at that scale. So for very cold things, Kelvins is helpful because it's not like negative hundreds of whatevers in the other scales. It's also helpful because when we use temperature as a measure of energy in calculations, we often can't handle negative numbers in that. It won't work in the calculation. So we have to start at 0. And so when we do those kinds of calculations, we'll always need to be in kelvins. The other weird thing about Kelvin that you might see here is that the Fahrenheit and Celsius scale are measured in degrees. So it's degrees Celsius, degrees Fahrenheit. But Kelvin is actually a unit, just like gram or meter. So we call that 100 kelvins, not 100 degrees Kelvin. And you can have millikelvins and kilokelvins and all that kind of stuff, just like you could with any other unit. So that's a little bit different as well. All right, let's talk about how to go back and forth between these scales. The easiest is going between Kelvin and Celsius. As you'll see here, the Kelvin and Celsius scales have the same number of degrees between the boiling and freezing points of water. So each degree is the same size in both scales. They're just offset by a certain number. That number is 273. So the temperature in Kelvin, I'll use a slightly different one here. The temperature in Kelvin is the temperature in Celsius plus 273. So all you do is you take the Celsius temperature, you add 273, and you got the Kelvin temperature. I think you had to do this in your pre-lab for Tuesday, right? So we're a little backwards here. You just add 273, and you want to go the other way, you subtract 273. So the temperature in Celsius is the temperature in Kelvin minus 273. Where it gets tricky is converting the other two, Celsius and Fahrenheit. And the reason for that is you have kind of two things to mess with here. Not only is it offset because 0C is 32F, but the degrees are actually different sizes. That's another nice thing that you can see in this picture. Between boiling and freezing water, you've got 100 Celsius degrees, but you've got 180 Fahrenheit degrees. So each Fahrenheit degree is smaller than a Celsius degree. That's like a unit conversion, like saying that a kilogram is bigger than a pound, and you need some number to go between those. It's the same thing with these. There are 9 Fahrenheit degrees for every 5 Celsius degrees. So we need a factor that kind of corrects for that, and then we also need this offset from 0. So the equations look like this. The temperature in Fahrenheit is 1.8, which is 9 divided by 5, times the Celsius temperature. And then after we do that multiplication, so you always have to do the multiplication first, then we add 32. And that gets us from Celsius to Fahrenheit. The temperature in Celsius, we're going to first subtract 32 from the Fahrenheit temperature. So do that first. And then divide by 1.8. So yes, they're kind of opposite, but because you have to both divide or multiply and add or subtract, you have to make sure to do it in the right order. So to check yourself on these, grab a calculator or your phone or something, and let's take the body temperature, which is 37 degrees Celsius or 98.6 degrees Fahrenheit, and try to plug those numbers into those equations and make sure that you can come up with the other number. So just try it on your calculator, put in 37 to the second equation, and then put in 98.6 to the third equation, and make sure you got the right numbers coming out, that it goes back and forth that way. When you think you got that, when that's working out, my phone says that outside right now, it is 87 degrees Fahrenheit. See if you can convert that into degrees Celsius and Kelvin using those equations. But 87. Everybody got those work out? Any issues? Some calculators have issues with this order of operations, so that's why we want to check that. Specifically with that second one, if you put in a temperature and then you just say minus 32 divided by 1.8, that's not going to come out right because most calculators are going to do the division first and then the subtraction, which will get you the wrong number. So make sure you go whatever number, 98.6 minus 32, enter, divided by 1.8. All right, so you got some temperature conversions for outside today? What is it in Celsius?
30.5.
30.5? That's what everybody got? All right. And then in Kelvin?
303.1.
Right. So you had 273, and that's all you gotta do. You can do that? All right. You do have to be able to do these conversions, but you don't need to memorize these equations. Not that they're not helpful in your life, but I will give them to you for the exams and quizzes. You just have to know how to use them. Your question?
Yeah, I was just wondering, do we always have to run to just one decimal place?
Yeah, this keeps coming up. We didn't go through the part in chapter 2 about how you decide how many decimal places to go to. So it's just kind of up to you in this class. We'll just, general rule of thumb, keep about as many decimal places as you started with. If you want to add one or take one away, that's probably okay too. There are rules for it. We're not going to go through them in this class. All right, good. So everybody's good with temperature conversions. That's great. So the way that we can use temperature, so temperature is not a direct measure of heat because heat talks about a change. Heat talks about flowing from here to here. But we can use temperature to measure heat because we can measure the temperature of something before a process and then after a process. And the difference in temperature is going to tell us something about how the heat is flowed. See how that might work? Before we do that, we have to talk a little bit about the units we use for energy. So these units are not measured of energy. These are measurements of temperature. So what units are measurements of energy? Yeah. So I heard somebody say joules. The joule with a capital J, that is a typical metric unit of energy. What else? Newton is a measure of force, actually.
Ohms?
Ohms is a measure of resistance. But if you're going in the electrical realm, you're close. What is the measure of energy, of electrical energy?
Watt.
That's power. Getting closer. What else?
I'm just eliminating all.
You got it. Volts, yeah.
Volts.
So the volt is a measure of electrical energy or electrical potential energy. Just keep saying things and just
elimination.
enough stuff comes out of your mouth, something's got to be right, right?
Yeah.
People use that strategy on exams too, like, well, if I just write enough, one of these words has to be right. All right, so we've got joule, volt, specifically for electrical energy. What else? What are some other measures of energy that you know about?
I didn't realize, but like horsepower in a car?
Yes, horsepower is power, I would imagine. Yes, so the energy in a car would be given in, I don't know how you convert to horsepower. Yeah, it would be one of these things, right? Anybody know how horsepower is calculated? We should look that up. That's interesting. Yeah. What else? Other units of energy. How do you measure how much energy you take in or put out? Calories, yeah. That's a big one. And then that's kind of the big ones. I'm going to put a star next to these two because these are the ones we'll focus on, calorie and joule. Volt is really specific to electrical stuff, so we're not really going to get into that here. Other one I would put on just because it comes up here and there is the BTU. Stands for British Thermal Unit. It's a weird, it's not weird. It has a specific measurement that we'll talk about in a little bit, but it's an English unit, and the way that it comes up is usually in things like heating and cooling of houses, like air conditioners and furnaces are rated in BTUs. Fuels are often rated in BTUs, like gasoline, that kind of stuff, energy content of gasoline. So that's where you might see it. We won't mess with it too much in this class because it's not really a measurement that we use. So does anybody know where that calorie unit comes from? Calorie unit has a very specific source, very specific origin. Well, we use it in nutrition, yes. But as an energy measurement, I don't know if anybody's read ahead or anything. 1 calorie is the amount of energy it takes to raise 1 gram of water 1 degree C. If you had 1 gram of water, and we know by the density that that's 1 milliliter of water, so just a little bit of water, and you want to take that water and raise it from, let's say it's outside, so 30 degrees to 31 degrees C, that takes exactly 1 calorie of energy. That's how much energy it takes to actually do that. And I think the British thermal unit comes from the same idea of it takes 1 British thermal unit to raise a pound of water 1 degree F. So it's like the English unit equivalent of that. But anyway, we're going to focus on this one. So 1 calorie raises 1 gram of water 1 degree C. And this is known as the specific heat of water. So the specific heat in general is how much energy, there we go, it takes to raise 1 gram of something 1 degree C. So for water, it takes 1 calorie to raise 1 gram of water 1 degree C. For other things, it will take more. So if water's specific heat is 1 calorie for 1 gram 1 degree C, if another substance had a specific heat lower than that, let's say like 0.2, what does that tell you about how it interacts with heat or how heat affects it? So if water is 1, it takes 1 calorie. Let's say I think aluminum is like 0.2. Let me grab a table from the book here so we can not just use made up numbers. Can't remember what page it's on. Here's some, okay. We'll put this thing in here. There are some specific heats. Can you see those numbers, or is that way too small? You can kind of see them. So water we've got right here. 1 means 1 calorie per gram degree C. 1 calorie for 1 gram going up 1 degree. And in joules, that's 4.184. You know, it's the same idea, just you have to do a unit conversion. So let's look at aluminum. I was pretty close. Aluminum is 0.2. So what does that tell you about the amount of heat it takes to increase the temperature of, say, a block of aluminum? Does that tell you it takes more or less heat than water?
Less.
Less, yeah.
5.
And that's our experience too, right? It's easier to heat up a piece of metal than it is to heat up water. It takes less energy to heat up that metal. If you put an aluminum pan on the stove and you turn it on, that aluminum pan is going to get really hot faster than water would inside that pan. Would you agree, probably? Especially if you have kind of a weak stove. And the interesting thing, if you see some of these examples, that most stuff actually has specific heats lower than water. Water is very unique in that. It has a very high specific heat. It takes a lot of energy to heat it up compared to a lot of other substances that we deal with. There are, of course, other things that also have high specific heats. Things like ceramics, like a coffee mug. That's why it kind of helps to cool your whatever you put your coffee or whatever that you put in the mug, because that heat flows out to the mug. But generally, water is kind of unique in its very high specific heat. All right, so let's talk about how we calculate energy based on temperature. If it takes 1 calorie to raise 1 gram of water 1 degree C, we can do problems like this. And we're going to do something like this in lab next week. Let's say we have 100 grams of water. "100 grams of water is heated from 25 degrees C to 65 degrees C. How much energy was used?" So how much energy was used to take all that water, that much temperature? Any guesses? Any ideas how you go about this? How you could figure this out? Remember back to that idea of that calorie. 1 calorie takes 1 gram of water up 1 degrees. So how many calories would take 100 grams of water up that many degrees?
65 minus
Yeah.
25, we need 40 degrees.
Right.
And for this 40 degrees, we need multiply. Thank you. 100.
Yes.
4,000. Oh no,
Yes.
1,000.
Yes. So were you saying the same thing? You kind of have to put them together?
Take the difference between 6 and 25.
Right. Yep. You're both right. So we're going to look at the temperature difference, or the amount of actual temperature that's changed. So that's going to be, we make this symbol delta T. That's the Greek letter delta for D for difference. That's the change in temperature is going to be 65 minus 25, which is 40 degrees C change in temperature. So we're not going up 1 degree, we're going up 40 degrees. And we don't have 1 gram of water, we have 100 grams of water. So each of those 100 grams has to go up 40 degrees. And that tells us that we're doing multiplication here. So we're going to take 100 grams of water times 40 degrees C and get 4,000 calories. Now, those of you who are looking really closely at this have noticed that this doesn't work out unit-wise. A gram times a degree C is not a calorie. There's something weird here. So there's actually a third term that we didn't put in here, which is that specific heat. So the specific heat of water is 1 gram per, or I'm sorry, not 1 gram, 1 calorie per 1 gram degree C. So that's how for those of you who are following units, and don't worry about it if this is confusing you, but the grams can cancel, the degrees C can cancel, and we're left with calories. So that tells us the calories. We usually don't, when you were doing the calculation, you were right to just ignore that because it's just 1. But if we were talking about a different substance besides water being raised a certain number of degrees, we would have to make sure to include that specific heat from the table. So if we were talking about aluminum going up a certain amount, we would have to put in 0.214 instead of 1. The overall equation then, the way that we usually write it, is Q equals mc delta T. Q is heat. M is the mass of the substance. C is the heat capacity or a specific heat. And delta T is the change in temperature. If we're talking about changing the temperature of water, then C is 1, and we just multiply the mass times the change in temperature. And that's the vast majority of the ones that we'll do, where we just find the change in temperature and multiply it by how much water is used. We do an experiment with this in lab called calorimetry. That's how we determine the amount of heat in, let's say, a chemical reaction. So remember I was giving you those examples, like you do a chemical reaction and it gets hot. So what you can do is you could do that chemical reaction inside a thermos or some sort of a device that doesn't allow heat to escape to the outside. And you measure the change in temperature with a thermometer in there while the reaction is going. You subtract the final temperature from the initial temperature, and then do that multiplication by how much water was it heated up, and then you know the amount of heat that was given off by that particular process. So we'll do some experiments like that in lab. One other little thing about these units that is a little bit confusing, so I'm going to say confusion alert. We've been talking about calories as this unit, and you've noticed I've been writing it with a lowercase c. There is another calorie with an uppercase c, and it is not the same. And that's really confusing because c's look the same, so you just have to not write it too big, or you're off by 1,000. So one big C calorie is 1,000 little c calories. Right, why? Exactly. It's dumb. So a better way to express that, rather than a big C calorie, is a kilocalorie or a kcal. Why don't they just go? So the only place that we see those big C calories is where? Anybody know? Food. If you look at your food label, it will have calories with a big capital C, and that's really kilocalories or kcals. That's not the little c calories that we're talking about, like the 1 gram 1 degree C thing. It's 1,000 of those. So don't make your C's too big, I guess is the moral of the story. Does anybody have a snack or like something with a label? I usually have one, but I didn't bring one. Can I borrow your? I won't drink it. I'll just look at it. I should do this as a trick. Just be like, does anybody have food? And then just eat everybody's food. All right, so let's see if we can put this thing up on the screen here. Whoop. Not focusing well. Can we focus it? There we go. Okay. So there's your label. Serving size 1 bottle. And you see big C calories, 250 of those. So that would be 250,000 little c calories. So that means that the amount of energy in this bottle, right, which is all comes from sugar, the amount of energy in it is enough energy to raise, let's say, 1,000 grams of water by 250 degrees. Which isn't actually possible because water can't get that hot because it'll just evaporate, right? Yeah.
When we speak about daily amount of calories, do we speak about those calories?
Yes.
Or
Yes.
should we speak about smaller?
No, we're speaking of these. But you'll notice.
1,200 calories those?
Right.
No. I think we need for a day, a woman needs around 1,000 and something. And
Kilocalories?
That's
or-
kilocalories.
no, it's calories. No, it's calories. Because,
No,
yes, I'm sure.
I don't think so. That wouldn't make sense.
Ah,
Because that would mean that because that 250 is kilocalories.
yes, there are too much calories in this.
Well, sure, but you can't say that one person needs
So small, right?
This
a
is,
thousandth of that, right?
So we speak about those.
Because we speak about these, yeah.
Okay.
So this is 200, one bottle of these has 250,000 of the little C calories in it. Right, yeah. Right, I'll take you all off the screen and see. Back to, yeah, so when we talk about the food calories, and I noticed on that bottle, actually, I should have pointed it out before I put it down, it said something about part of a 2,000 calorie a day diet, and they used a little c when really it should have been a big C or a K-cal, yeah. And I think in other countries, it's K-cals, right? I think the big C calorie is unique to here, so that you avoid that confusion elsewhere. All right, the other thing that we can do with this is we can calculate, and we'll do this in lab next week as well, we can calculate the amount of energy in our food based on the energy of certain components of the food. What are the three major categories, I guess, of nutrients in food?
Fat, protein, carbohydrate.
Yeah, fat, protein, and carbohydrates. Have you heard of those mostly? Okay, yeah. So let's look at the energy content, broadly speaking, in averages of those what we call macronutrients. Fat has 9 kcals per gram. Protein is 4 kcals per gram. And carbohydrates are about 4 kcals per gram. Now, this is on average across the whole category. And speaking of the entire energy potential from a molecular scale, if you have these molecules and you burn them carefully in a calorimeter, this is how much energy content we have. This is not necessarily translate to exactly how your body would use it, or, you know, as you've probably learned in nutrition classes and things, it's all very complicated. Your body uses them in different ways. But from a standpoint of the actual potential energy contained within these molecules, this is about correct. So if we have a food, a particular food, that has 37 grams of carbohydrates, 19 grams of fat, and 23 grams of protein, we can multiply it by these factors and get a pretty good idea of the caloric content of the food. So we could take 37 grams times 4 kcals per gram. Grams cancel, and we get 150 kcals. Then we could take that 19 of fat, multiply that by 9 kcals per gram, and get 170. And then we could take that protein, 23 grams times 4 kcals per gram, and get 92. Add all those up together, and this food would have 412 kcals total. And if you try that on your labels of whatever snacks you have, you should get the same number as what's on the label, minus some rounding error perhaps. But these are going to be, those are called, those are the 3 main categories of nutrients, because those are what provide most of your energy in the food that you eat. The other things, the minerals and stuff like that, don't really provide energy. All right.
So you rounded on some and not the others?
Did I?
Yeah, it should be 148 to 150, 171, 170.
Oh, yes, you're right. I did so that there are two significant figures in each one, but you could do it unrounded.
Okay.
You can keep it the same, however you want to do it. It should be right around the same number still, right, in total.
Yeah.
All right, so there's some practice in the homework of doing that, and we'll do it in the lab next week also. All right, so for the last part, let's kind of look at the effect of phase changes and heating curves. So let me grab a picture from the book here. Uh-oh, slowing down. There we go. All right, this thing here is called a heating curve. And I will show you how we use it and what we can learn from it. This is a heating curve for water. And a heating curve is a way to graph the temperature versus the amount of heat put into the system. Remember, based on the specific heat stuff, temperature and heat are not the same. You can put heat into a system and not change the temperature, or you can put it in and change the temperature, and depending on what you're changing, it could be different amounts. So something like this helps us understand how that happens, especially going through phase changes. If we start at down at the bottom right corner of this diagram, this one starts at minus 40 degrees C. And at minus 40 degrees C, water is in what form? Ice. It's ice, right? As that heat increases from minus 40 to 0, as we add heat, we increase the temperature of that ice from minus 40 to 0. And that's what this graph shows us. We add some heat, the temperature increases. At 0, something happens. The amount of heat increases. We put in more heat, but we don't change the temperature. So what's happening there? I mean, it says, but it's melting. What that tells us is that for ice to melt requires energy to be put in. So you bring ice to 0 degrees. If that's all the energy that's there, it's going to stop. You can have 0 degree ice. You can have 0 degree water. You actually have to put in or take out energy to make that temperature change. So is melting ice an exo or an endothermic process? When ice melts, where does the energy? Does energy go from the surroundings into the system or to the ice out to the surroundings? We got some back and forth. So why exo? Start with why exothermic?
Because it's turning, it's dissolving, it's melting, it's turning into a different form of matter.
True. So then why endo?
Heat absorbed. So we need heat to put in.
Yeah.
Endothermic.
Okay. Anybody else want to throw in an opinion here or there? So yes, it's changing from a solid to a liquid. What we're concerned with when we're deciding endo or exo is which direction is the heat flowing. Does it require heat in to melt that ice? It does, right? So that melting ice actually is an endothermic process. It's sucking in energy from the surroundings. Now, that process is also spontaneous, which is a whole different thing that we'll get into later, which means that there's a kind of a driving force for it. So it can actually suck energy in. You don't have to necessarily apply the energy like on purpose. And some examples of that, has anybody ever made ice cream with ice? Yeah? So what do? Yeah, you have to use melting ice to cool the ice cream. So if you make your ice cream blend thing, and then you pack it with ice, and then you dump salt in to force the ice to melt, and we'll get into why that is later. But it forces the ice to melt, which sucks energy away from the ice cream and actually cools it down more than it could be otherwise. So that's this endothermic process. All right, so we've sucked in this energy and now we have liquid at 0 degrees. Now we add more heat and we're heating up the water, the liquid water. Heated, heated, heated. And then at 100, something else happens. It doesn't go into a gas until we put in a whole bunch more heat. Everybody see that? And so there's another endothermic process, right? The thing that always surprises me about this, and the thing that I think is striking, is that the amount of heat for a certain amount of water to take, whoops. I don't want to do that. Go down here. So this is the amount of heat that it takes to heat water from 0 to 100 degrees. And then this is the amount of heat that it takes to boil water without changing the temperature. So you have 100-degree liquid water, and then you have 100-degree water vapor, but you've put in about 8 times as much energy to do that. So it takes way more energy to go from 100-degree water to 100-degree water vapor or steam than it does to go from 0-degree water to 100-degree water. A lot of energy to break up those bonds, and that's called the heat of vaporization. And that takes a lot of energy. That's why you may have experienced this. If you ever put water on a stove to boil, anybody ever done that? Hopefully, maybe. It gets hot pretty fast. It doesn't take long before you don't want to stick your hand in it anymore. But then to actually boil, it takes a while. And so you keep thinking, oh, this water's been hot for a while. Why is it not boiling yet? Well, it needs a lot more energy from the stove to actually break up those molecular interactions and actually boil. And that's why. So one other thing we can learn here is that if you look at these pictures, here's solid water all kind of packed together. The water molecules are all packed together. In liquid water, they're actually closer together, but they have a little bit more freedom to move around. That's the liquid. And then in the gas, they've separated from each other. But notice that the H2O molecule is still intact. When you boil water, you don't break up that H2O molecule. So that energy has nothing to do with the strength of the bonds inside the water molecule, because those bonds aren't affected by the boiling. It's the force that it takes to actually separate the water molecules from each other. But the H2O units actually stay intact. And we'll get into that in a couple chapters when we talk about bonding and all of that. So let's see how we can use a heating curve for a substance that we don't necessarily know about to make some decisions about its properties.
So we get the same energy for melting and for heating and for water, but it just takes more time.
No, it takes more energy. This is not time, this is energy or heat absorbed. So it takes much more heat to boil than it does to melt. And then, by the way, we should also say, once you get to the gas, then you can just heat up the gas as usual. Also, this is a little bit harder to see, but you might notice that the liquid water has a little bit of a shallower slope than the ice. Anybody see that? Like this is kind of like a steeper hill than this. That's a reflection of that specific heat. Liquid water has a specific heat of 1 calorie per gram degree C. Solid water actually has a lower specific heat. So it's actually easier, it takes less energy to heat ice up than it does to heat water up. And water vapor as well heats up more easily, has a little bit lower specific heat. And that's why there's the slight difference in slope there. So I'm going to pull out a problem from the book just to kind of show you what a book problem or exam problem might look like that uses these ideas. This is one we used in the other class too. Sorry, there's another part to it on the next page, so let me grab that too. All right. So here's a heating curve for not water. This is for chloroform. Chloroform is a solvent. Its formula is CHCl3. We use it a lot in organic chemistry for various things. You might know it as like the old put it on a rag and like knock somebody out thing. That's not a good idea. Don't do that. It's really bad for you. It's carcinogenic and you don't want to inhale it. I don't think people had their victims' cancer risk in mind when they were using that, but anyway, we just want to use it as solvents. What?
If only they took chem.
That's right. If only they took chem, they would find a better anesthetic for knocking people out. Anyway, here's a heating curve for chloroform, which is going to have similar properties to water, and then it has a solid and liquid and gas phase and all that. But it's going to have some different heat amounts and things like that. So see if you, with people around you or on your own, however you want to, see if you can answer these 4 questions. What's the melting point of chloroform? What's the boiling point of chloroform? What are those segments, A, B, C, D, and E, solid, liquid, gas, melting, or boiling? And then what is the state of chloroform at these 4 temperatures, solid, liquid, or gas? So you're going to have to look at that graph and compare it to the heating curve of water, or how we thought about the heating curve for water. And actually, it might be easiest to do part C first, where you identify those segments, and then go back to look at the other parts. If you think you have some answers, just look around with people next to you, talk to each other, and see how you agree or disagree. If you feel like you have similar ideas or not.
Oh, yeah. Right, yeah. You are right. Yeah.
Or would you all say it was the melting point of chloroform?
Oh, yeah. Yeah.
But what temperature would you say that is?
70.
Like -60? Yeah, or a little below, maybe -62 or something. It looks like it's just below that line, maybe. Yeah, something around there. What about the boiling point?
62 plus.
It's really difficult.
Yeah, like around here. So just below, maybe like 50 or something. Right around there, maybe 50 or 60. Yeah. You could, and if you were doing this on paper, you could, take a little piece of paper and kind of see where about it comes in. We're right around there. Yep. Let's identify the segments. So what's A, B, C, D, E?
Yes.
Wow, everybody got those. Okay, good. Felt like a elementary school teacher for a minute or something, like calling it out, and then everybody called it back. And then at the following temperatures, were there any discrepancies or controversies about this, or did you all pretty much agree on what the states were at these different temperatures?
It's just -40 is going to be liquid.
-40? Yes, because that would be right around here, and that would be on that liquid curve.
So as water is going to be ice.
Well, it's neither because it's chloroform, but it's going to be liquid chloroform. Yeah. Liquid chloroform. So yeah, this would look like solid, liquid, gas. Okay. Yeah.
Oh, it's good for 5.
Oh, okay. Good job. Yeah. So that's how we'd look at a problem like that. All right. That pretty much takes care of what we're going to talk about with energy. Next time on Tuesday, we're going to look at kind of an interesting case study of this, of how we can use some of these ideas, and then we'll move on to our next chapter. So have a great weekend. Tuesday, don't forget, we'll have a quiz on all this stuff and the unit conversions from before.
What quiz? It can be like tests or they have to answer questions. How to quiz ABC.
Yeah, kind of a mix of stuff. Mostly it'll be working out problems, but yeah, just like the homework. I'll make it just like the homework. And then lab on Tuesday, make sure you're dressed appropriately because I think it's still supposed to be hot on Tuesday, so make sure you have the right clothing and that you have the pre-labs done before coming in on Tuesday. And have a good holiday.